Morning, guys. So I'd like to give you a lecture on 9.1, which is momentum and impulse. Now, momentum is quite a fascinating topic, and I'd like just to start there a minute and just give you a bit of history, actually. So, those of you who've played sports will know that if you've got like a really, really like fast person running towards you, if you're stationary and they run into you, it's going to hurt, right? Also, if you've got like a larger person on the sports field running towards you, a little bit slower V, it still could hurt quite a lot. But if any of you have played rugby, you will know that if you've got a really big, heavy guy running quickly, that is going to hurt the most, right? So that is going to hurt like a lot. Okay, you might even go out, right? So what's that all about? Well, let's talk about Isaac Newton for a second. So Isaac Newton, he was the first person to realise that a force was needed to change the velocity of an object. And he realised that the effect of a force on an object depended on its mass, as well as the amount of force. And he defined this thing called momentum. Now, what momentum is, actually it's an equation that's equal to the mass of an object multiplied by its velocity. So now you can see why people with like really who are heavy and can move quickly are best at, like for rugby, because they can absolutely destroy people and tackles and that. Now, momentum is mass times velocity. Let's just have a quick look at the units. So mass is kilograms. Velocity is meters per second. So very simply, momentum's units is kilograms meters per second. And we're happy with that. So, although Newton did all this 300 years ago, we're still using this now. It's stood the test of time. I think it's absolutely brilliant. Now, we still use Newton's laws to launch rockets into space and all this kind of stuff. One thing to say on momentum, it is a vector, because we've got a scalar here, and we've got a vector here. So momentum is a vector. So it has a value and a direction. So we have to remember that. It's very important. One of the best laws we can apply is the conservation of momentum, but we're going to get onto that later on in another video. So for example, let's just do a very quick example from the book. If you've got a ball with mass 2 kilograms and you can get it up to a velocity of 10 meters per second with a momentum that has got momentum of 20 kilogram meters per second, that's got the same momentum as a person. It's got the same momentum as a person of mass 50 kilograms moving at a velocity of 0.4 meters per second. Again, they both have exactly the same momentum. So that's just to kind of show you how the momentum equation can be applied. Now let's just have a quick recap of Newton's laws of motion. So his first law of motion, Newton's first law, an object remains at rest or constant velocity or in uniform motion. unless acted on by a force. Right, so we've got that. So we need a force to change the momentum of an object. It's because we're going to change the velocity. If we change the velocity, we change the momentum. Now, his second law is often is often used incorrectly, and I want to talk a bit more about that. So, actually, second law is not F equals ma. People often say that. It's the rate of change of momentum of an object is proportional
Welcome back. How can I help you?
I don't know what I've just done. Something's talking to me. The object is proportional to the change to the resultant force. The rate of change of momentum of an object is proportional to the resultant force on it. So let's just take a look at Newton's second law. So force is proportional to the rate of change of momentum. So we can just say that F is equal to the change in time. So force is equal to the change in momentum over the change in time. So it's the rate of change. So where these little funny triangles mean change in. So some of you may be thinking, well, hang on a second, up here we had a proportionality, and you've jumped straight in there, Steve, with an equal sign. The way we get around that is you could put a k in this equation, but we make k equal to 1. So you could do F equals k delta mv over delta t, but we make this k thing equal to 1 by the following. We define 1 Newton that gives an object of mass 1 kilogram and acceleration of 1 meters per second squared. So if we do that, then we get rid of k and everything's happy. So sometimes physicists do this, they make their life easier by defining stuff. Anyway, I want to go back to this equation because it's quite a cool equation. So we've got F equals the change in mv over the change in t. Now, I'm just going to go off a bit on a mathematical side note for a second. And we can kind of say that if m is constant, now the reason I'm saying if m is constant, because in reality m could be a function of t, and v could be a function of t, or velocity could be a function of time, like things speed up. Mass could also be a function of time. For example, in a rocket, it's burning fuel, it's losing mass. So we need to be very careful what scenarios we're applying this equation in. This equation here always holds. This is always true. So let's just have a look. So if m is constant, then let's just have a look what happens. Now I'm going to quickly dive into something called the product rule of differentiation, because what we've got here is a little bit of a differentiation. So I'm going to do this over here. So if we've got f equals dmv by dt, that would equal m dv by dt plus v dm by dt. So that's the equation we're working with. Now, if m constant, so if m is constant, then this second part here gets crossed out, and we are left with m dv by dt. Well, what's the rate of change of velocity? ma, isn't it? So if m is constant, that just equals ma. So we're left with f equals ma, which is what you're used to. So, but we need to look at the other scenario. What if v is constant? So that means, so for example, if v is constant, that means, say for example, we've got a rocket which exerts some hot gas at constant speed v, then, and we've still got our equation f equals m dv by dt plus v dm by dt, then that means that that bit's going to go. So our f is going to equal v dm, or change in m over change in t, and that's our other equation, where m dm by dt is the change of mass per second. So we've got f equals rate of change of momentum, is always true. We've got f equals ma, which is true for constant mass. And we've got our second equation, f equals v dm by dt. Sorry, delta m over delta t, which is true for constant v. Now, where this v is something like gas expulsion. So these are our two equations. And this equation is used for where things change in mass. Now, at the start, I said this was momentum and impulse. And I've talked about momentum. Now, I want to talk about impulse. So, you're happy that F equals change in momentum over time. Now, don't forget that if you've got the before and after momentum, you can just put it in and you've got the time. So, say for example, you've got, if it obviously m's constant, if an object like slows down, you might have an equation that looks a bit like this, where these are velocities. So it's perfectly reasonable to just, if you've got the figures, just put them in. Like changing, if you can work out a change in momentum, then do it. And you've got a change in time, you can sort that. Now, what is an impulse? Well, it's quite strange, really. All we do is we just rearrange this equation. So if we multiply both sides by delta t, we get F delta t equals the change in momentum. So, and we call that this F delta t business here. This is just the impulse. What is it and why do we use it? Well, there's like a, the reason we use it is because, say if we, quite a common graph you might see is a force time graph. Like say if I exert a force of 20 newtons, I don't know, or say this is like 20 newtons for a time of like 3 seconds or something, right? That's 20 newtons and this is like 3 seconds down here, right? Let me just make that a bit clearer. So 20 newtons, 3 seconds. The area under this graph here, so the area is equal to F delta t, which is the impulse, right? But that's also equal to the change in momentum. So you know very quickly that the change in momentum for this particular scenario is 60 Newton seconds, or to use the units of momentum, 60 kilograms meters per second. So let's just do a quick worked example. And the worked example here is, say worked example, so a force of 10 newtons acts for 20 seconds on an object mass 50 kilograms initially at rest. So A, we want the change in momentum. And B, we want the velocity at 20 seconds. So, for part A, you know that Ft equals change in momentum, which in this case equals 10 times 20, which equals 200 Newton seconds. And for part B, we are looking for the velocity at 20 seconds. You know that force equals the rate of change in momentum. Change in momentum over change in time. So, what's the change in momentum? Well, it is m times the, oh dear, what have I pressed? It is the mass times the final velocity minus the mass times units of velocity over the time. Now, we know that the initial speed was 0. So we know that the final momentum is the complete change. So therefore, we have the force on the object. So force times the time is equal to m times the final speed. So let's put those numbers in and rewrite divide by m. So we've got 200 over the mass, which is 50, and equals the final velocity, which is 4 meters per second. So that was a lecture on momentum and impulse, and I hope it has been useful.